Hello and welcome to a video on Introduction to Statistics, where we are going to do a couple of examples from this, my favorite book on statistics, Statistics for Psychology. Strongly encourage that you have a look if you're interested in statistics at all. Regardless of your interest in psychology, the concepts are very applicable. We're going to do a couple of examples on specifically significance and power. I'm going to use for this video Microsoft Excel as a glorified calculator just for the convenience of having the space to do various calculations and see them at the same time. But you can do this with any calculator by hand, all of those things. So just make sure that you have a good idea before coming into this of the normal distribution and the basic ideas of hypothesis testing and converting a raw score to a z-score, things like that. So let's have a look at number 15, where we'll do a couple of these C, D, and E. In a planned study, there is a known population with a normal distribution. Mu is 0, sigma is 10. What is the predicted effect size, D, if the researchers predict that those given an experimental treatment have a mean of a variety of numbers here? So we're specifically going to look at, like I said, C, D, and E.
Welcome to MathCats, where we aim to better understand mathematics. Join us weekly for discussions on elementary, high school, through to university math. You can request the next topic by leaving a comment on our YouTube channel or by emailing us at mathcats314@gmail.com. And as always, remember to like and subscribe. Thank you.
So for this, we have to remember, well, what is the formula for effect size? I'll have it here. This is in the same book. We'll mainly use this formula, 6(1), where the effect size is the difference between two means over the standard deviation, giving me an indication or a measure of how significant this treatment is. So let's have a look at that. So I've set my spreadsheet up for convenience. You can copy this. I have the habit just to let things stand out using yellow cells for things that are given to me already in the question and green for calculations that I am going to do. So we're going to do C, D, and E. So in the first one, so mu is 0 and sigma is 10, and we're simply going to use that calculation. The difference between the predicted mean, let's go back to the question perhaps if you need to, predicted mean, which is in C, -2, versus the mean of the distribution of the population, and then of course divided by sigma. So our calculation is going to be very simple. I'll put some brackets in there. In Excel, I start with an equal sign, telling Excel that I'm going to do a calculation or a formula. So I'm going to take -2, which is the predicted mean, minus, now in this case I know it's 0, but it could be something else in another question, the value in that cell, and close the bracket and divide by sigma. And we get -0.2. So it's a negative effect size, lowering from the population mean. And we can go look at, for example, the table provided on page 186 that give you sort of the conventions for when we call it a large effect, a medium effect, and a small effect. So this one will be a small negative effect. So small negative effect And that's C, done. In D, let's remember what was the predicted mean. Oh no, I'll go back to page 223. D is 0, so I expect it to be 0, of course, but let's do the calculation anyway, just for practice, in case you need to practice the spreadsheet. 0 for the predicted mean, and minus mu, close my bracket, divided by the sigma number, and of course I get 0. So we could say here, no predicted effect, or very small. These are just measures to indicate what we expect. And lastly, in E, we have 10. So difference between 10 and the mean. I know these calculations are very simple. It is an introduction to just practice using the formula, thinking about effect size, and so on. Divided by sigma, and we get 1. So looking back at the table, anything from 0.1 is considered large. So large effect or large positive effect. All right, so a little practice question there on effect size. Then we'll move on to number 16 in that same chapter. Let's look at number 16 where we will do B and C. Let's read 16. In a planned study, there is a known population with a normal distribution. This time mu is 17.5, sigma is 32. No, not 32, 3.2. Decimal points matter. What is the predicted mean if the researchers predict a small positive effect size, medium, and a bunch of different effect sizes? We'll do, like I said, B and C. So in B, a medium negative effect size. Let's go back to that page 186 where the table is medium negative, so negative 0.5 is my effect size. So I have things laid out here. I'm going to put in negative 0.5 for the desired effect size. Mu was 17.5, sigma 3.2. 17.5, sigma 3.2. So now I have to take that formula and let's maybe get us some space to write. Let's scribble some stuff. So now our formula was D equal to mu predicted minus mu of the population over sigma. So now I have the effect size and I'm looking for the predicted mean. So I'm going to multiply both sides by sigma and essentially solve for mu predicted. So mu predicted is mu plus sigma, we can have a little times symbol there, times D. So that's going to be my calculation. Let's remember that as we go to our spreadsheet. So it's going to be mu plus sigma times D. And we get a 15.9. Now, I should have two different D values here, but I'll just write this separately here because this might change. If I now change the D, the effect size, this calculation uses that cell, so it'll update as well. So I just write it somewhere else. In part B, where am I now? B, question, B, there we go. B, that was B, medium negative effect size. I also want to do C, an effect size of D, 0.4. So now the spreadsheet makes it so convenient, I can just put in here 0.4, and the calculation you see there will update, and I can put that next to, let's delete that, I can put that next to the C answer. So another benefit of the spreadsheet, you can use spreadsheet for many things, but one thing is just a glorified calculator. And making calculations, especially when I do the same calculation over and over with slightly different numbers, makes that very convenient. All right, then lastly, I want to do number 11. Number 11. Let's go back to the question. 11 is on the previous page where we'll calculate some power. Let's read it first. Based on a particular theory of creativity, a psychologist predicts that artists will be greater risk takers than the general population. The general population is normally distributed with a mean of 50 and a standard deviation of 12 on the risk-taking questionnaire the psychologist plans to use. Mean of 50, standard deviation of 12. Psychologist expects that artists will score on average 55 on this questionnaire. The psychologist plans to study 36 artists and test the hypothesis at the 0.05 level, so alpha is 0.05, 5%. What's the power of this study? We might need to sketch the distributions to figure this out, and I'm not going to do the whole explanation portion. So let's see, what is the power of this study? So we have 36 in our sample, and our alpha is 0.5. So let's go, before we go to the calculations here, just try and visualize what's happening here to help us a little bit. Let's go here, move this up a little bit so we don't worry about those things. So we have our essentially null hypothesis. The distribution is a normal distribution. It's going to be a little wobbly here, but we have our bell curve, somewhat symmetrical here. And that is positioned at mu equal to 50. Now our cutoff will be over here, cut off, so that the tail here is alpha, which is 5% or 0.05. So first we need to find out what is this cutoff z-score. So for that, you can look it up in the table, or Excel can be very handy. I'm just going to delete that to redo that. So I put in the alpha that I want. And now the spreadsheet has the normal distribution function built in. So I can search for normal, maybe. Don't have to search for all the words. And I'm going to scroll down sometimes. I don't find what I'm looking for. Normal distribution. And there's also a very nice description here. Now we're working with a standard normal distribution. The z-score is where that comes from. So I don't have a z-score and looking for the probability. I am doing the inverse where I have a probability, namely alpha, and I'm looking for the z-score that gets me this alpha, right? Now the way that is set up is it's cumulative, so it's going to be the left side of this cutoff line, and I specifically have a right-tailed look at the question, because I am, where is it? We're looking at if the artists will be greater risk takers. So specifically, we're checking the hypothesis. Let's write that down up here maybe. that from the basic population being, oh, not 0, undo 50, our alternative or research hypothesis is that it's specifically greater than. So we have a one-tailed test on the right. So because I'm on the right, this area over here is therefore going to be 1 minus alpha. And so when I choose this, I'm going to pick 1 minus the alpha provided up there. Now, I could put in 0.05 because I'm not going to change it, but it's good to get used to using cell values. And if I ever want 1%, I'll just change that to 0.01 and the alpha and the z-score will update. But that's not what we have, so 0.05. So that's my cutoff. So let's draw that in here. So that is, what did I say it was? 1.64. And I'm also very accurate. Usually when I look it up in tables, it's not that accurate because they have a lot of numbers to show. It's accurate much more than a table would be. So now I need to see, well, okay, what is the raw score that corresponds to this cutoff score? Now that's going to be very similar to what we saw before in terms of the formula for sort of the changed formula for effect size, where I'm looking for the predicted mean. Because remember, the z-score is my raw score minus mu over sigma. So now I have the z-score and I'm looking for x. So x is going to be mu plus sigma times the z-score. So I can calculate the corresponding raw score in my spreadsheet. Let's just put in the mean here is 50. The predicted mean is 55. Sigma was 12. And remember on my my comparison distribution that I'm using in my hypothesis testing, I'm using the distribution of means. So I need to adjust the sigma to the distribution of means. Mu is the same. We have 36 people in our sample. And so the standard deviation of this distribution of means is going to be the standard deviation of the population divided by the square root of the sample size. So I have this SQRT function for the square root. I could also search in the function insert function window for square root, and it'll come up, and that's it too. Very convenient. Doesn't have to be that clean. So I want to calculate x from the z-score. Z-score in this case that I'm going to use is 1.64485, and using the formula that we wrote down, remember this one. Oopsie, let's move it a little bit over there. Mu plus sigma times the z-score. I'm going to calculate that. Mu plus, let's just double check here. Although, remember, it is the sigma of the distribution, which is this 2 times the z-score. And we get 53.3-ish. 53.3-ish. Let's write that in, picture what is happening here. 53. No, I don't want to use one decimal. Was it 2.8, I think? I can't remember now. Let's have a look again. 2.9, I guess, if I round to 2 decimal places. A lot of screen switching here. 53.29. All right. So that'll be the raw score that corresponds to this cutoff when I'm going to reject the null hypothesis if I am past this cutoff, whether I do it by a z-score comparison or a raw score comparison. Past this, to the right of this cutoff, I'm going to reject the null hypothesis. To the left, I'm not going to reject the null hypothesis. So if I now draw not that high, undo a little lower. If I draw the distribution under the research hypothesis with the predicted mean, which would sit here at 55, that is going to be a slightly shifted, that's a wobbly bell curve. Whoa, no, at least try and get some symmetry here, my friend. There we go. It's close enough. Ooh, deceptively hard to draw without seeing your hands. Like so. That's going to be slightly shifted. And because my cutoff was 53.29, the predicted mean was 55, it's necessarily going to sit a little bit to the right of that cutoff raw score. That's over here at 53.29. So if the null hypothesis is false, it's not true, the research hypothesis is true, this is actually the distribution that is happening. But I'm going to reject it for all of these scores. And that would be the correct decision. If the null hypothesis is false, and this is actually true, this is my best guess for what is actually happening, I'm going to reject as soon as I get an X, a raw score past 53.29. But in truth, the probability of that happening is based on this curve over here. So that is going to be what we call the power. Another way of saying it, that if the research hypothesis is true, the null hypothesis is false, I am not going to reject it for this twirly bit over here. That's my probability of not rejecting, when I actually should. Because left of the cutoff is when I'm going to not reject it. But if I actually should, then my probability is over here, and that is called beta. That is called a type 2 error. The probability of not rejecting the null hypothesis when I really should, when it's actually not true, that's a mistake, right? When the research hypothesis is true and there is a shift in this in the distribution by way of the mean, shifting to the right, I should actually reject the null hypothesis. It's not true. It's not exactly 50. The artists are more likely to take risks. So to calculate these areas, if I have one, I have the other, because they add up to 1. I will use this distribution with a mean of 55, same standard deviation. So that means if I use my table, maybe we want to convert this to a z-score. What is the corresponding z-score for 53.29 in this distribution? Okay, so that paints the picture. Let's have a look. So now I have this 53.2897 as the input, and I'm using this predicted mean for the top distribution to calculate the z-score. Now remember, we did it over here. We showed those two formulas over here. So that's the top one now that I'm going to use. So let's put that in. It is the raw score minus the mean for that distribution is 55 divided by the same sigma m for the distribution of means, which these are. Did I press equal by accident? Let's just double check. No, I didn't actually finish it, right? Divided by this guy over here, enter, and I get negative 0.85515. Now, you don't technically need to find the z-score in Excel, but let's go back here. But if you're going to use a statistical table that you're going to look it up, it's by z-score. Only the normal distribution is, the standard normal distribution is given. When I'm looking up in a book, what is it? Negative 0.86. Let's write that down here. Where's my pen? My pen has decided to not play along. That's okay, I don't really need it. Negative 0.86. So now I need to look up for this beta, which is the left area, called beta, type 2 error. Now I'm going to look it up in a cumulative normal distribution, standard normal, looking at the z-score. So let's see. I'm going to insert a function. So I click up on this insert function, and maybe I don't know exactly what the function name is. I'm just going to search for normal, and you get used to what you're looking for. We're looking for a normal, standard normal distribution. So I'm looking for that S. So which one of these is it? Distribution or inverse? Well, the distribution has a description here, taking the z-score, and yes, it's cumulative, meaning I'm looking for the area from the left sweeping up to that line. Inverse is the reverse of that, taking the probability, the area under the normal curve, and giving me a z-score. That's not what I want. I want the distribution one. And then if I use the insert function, it will actually sort of ask me for the different inputs here. The z-score is this one. Cumulative, I'm going to go with true because I'm looking for that whole area that sweeps from the left. And we get 0.19623. Now, I would write it on there, but I can write with a mouse, but it looks absolutely terrible. So let's not do that. So that's this area over here. What was it? 0.19623. Then the power is simply 1 minus that. And my power is 80.377%. And it'll round it usually as a default to the nearest hundredth. So that's the power of this study, that I'm making the correct decision in terms of the research hypothesis being actually true. The null hypothesis is not true. The probability of me rejecting it, remember, past this cutoff is when I'm going to reject. But if it actually did shift, the probability of making that correct decision is actually much greater, and that is what we call the power. So there we go, a couple of examples on significance and power. See if that makes sense. Feel free to ask questions. Until next time.